Yeah, very good.
Okay, to zamienimy może.
Okay, so can I start?
Yes, please.
So, hello everyone, and thank you for inviting me here to give this seminar. I'll talk today about certain topics at the intersection of ergodic theory, combinatorics, and number theory, and which have to do with studying the limiting behavior of multiple ergodic averages, in which the iterates will be polynomials, and these will be averages on systems of commuting transformations. And most of the things that I'll talk about today is based on joint works with Nikos Frantzikinakis from the University of Kuca. So let me start with the setup for the talk today. What we'll look today at is the limiting behavior in two of these kind of averages, where we have some standard probability space. We have measure preserving transformations on the space, which more importantly commute, so the order of taking transformations doesn't matter. I'll also assume them to be invertible because sometimes I'll need to evaluate them at negative numbers. And together all of these things I'll refer to as a system. And the iterates that you see here will be polynomials with integer coefficients and also with zero constant terms. And I'll refer to such polynomials throughout the talk as integral. And lastly, all the functions that I'll look at will be bounded in L infinity. And you can assume without loss of generality that they are bounded by 1 in L infinity in order, if you like.
I presume that this action T on F is composition of F with T.
Yes, exactly, yeah. So just to write it, TF is always just F composed with T. Yeah, so that's the setup. And why are these objects even of interest? The main reason to study them is because they appear in the polynomial Szemerédi theorem of Bergelson and Leibman. So in 1996, Bergelson and Leibman proved the following very general result, that if we have integral polynomials and a system and a measurable set of positive measure, then the following average has a positive limit. In other words, the following intersections have positive measure on average. And this result generalizes an earlier theorem of Szemerédi, which concerns arithmetic progressions rather than these polynomial objects. Then Szemerédi's theorem has been proved again using ergodic methods by Furstenberg, and in doing so, Furstenberg initiated a very fruitful cooperation between ergodic theory and combinatorics. And this theorem of Bergelson and Leibman is one extension of the Szemerédi theorem for which no other proof exists apart from ergodic proofs. So it's a result that illustrates the strength of ergodic methods in dealing with questions in combinatorics. The reason why it's of interest to combinatorics is because of this corollary, which is purely combinatorial and can be deduced from the ergodic statement from using the Furstenberg correspondence principle. And this corollary says that if I take any integral polynomials and any choice of directions in as I didn't explain, but of positive upper density, which means that so a set satisfying this condition so each subset of ZT of positive upper density contains a polynomial progression of the following form for some non-zero element n. So what this condition means is that the set A occupies a positive proportion of all the elements of ZT.
Could you lift up a little bit the camera to for the formula?
Sorry.
Thank you. Thank you.
No problem.
Not too much. It's okay.
Yes.
This is good. Very good. Very good. Thank you.
In this theorem of Bergelson and Leibman, it corresponds to the case when f1, f2, fk equal to characteristic function of
Exactly.
a, right?
Yeah. Yeah. And so, for instance, to make this a bit more explicit, this theorem tells, among others, that each subset of Z2 of positive upper density contains a configuration of the following form. And if we just care about the single-dimensional version of this, so with d equal to 1, then we could take all the transformations to be the same. But if we want the multi-dimensional version of this theorem, then we have to look at commuting transformations, and this is the motivation for studying systems of commuting transformations and corresponding polynomial ergodic averages. So the next question after recurrence, because this result that I stated here is about certain form of multiple recurrence, the next question that one can ask about is about convergence of such averages. And in a spectacular paper about 10 years ago, Walsh proved that these kind of averages always converge in L2 whenever we have a system of commuting transformations and integral polynomials. In fact, Walsh proved a much stronger result where he allowed the transformations to form an impotent group. And so we know now that this converges, and this very strong result came after a series of partial results which handled the case of a single transformation or when all the polynomials were linear. So in the case of a single transformation, this has been proved about 7-8 years earlier by Holst and Cracow and independently by Ziegler. Then for polynomials, it has been proved for a single transformation by Leibman. In the case of commuting transformations and linear polynomials, this has been proved by Tao, Austin, and Holst. But no one knew how to extend this to polynomials until Walsh came and gave this very big, very broad result.
So is this true for, say, commuting contractions on a Hilbert space? Because in the end you ask about convergence in L2. Okay?
Yeah.
So you could ask the same and you just take the commuting contractions in the Hilbert space, you forget the dynamical picture.
I don't know if anyone has tried to prove it. So this result, if I remember correctly, doesn't use very strongly the dynamics. It uses some very complicated induction scheme, but I don't know if anyone has tried to prove it in a different set.
But you can ask the question nevertheless.
Yeah, well, you can try, certainly. Yeah. And so everything that I'll talk today in this talk will concern L2 limiting behavior, but let me just point out that when we are interested in pointwise convergence, then such results are only known in several very limited cases. So for instance, Bourgain proved that we have a single polynomial convergence. Sorry, we have a polynomial convergence for a single average. Are we okay?
Yes. So, please say something.
I'm saying something.
Okay. So now it's no resonance.
Good.
Yes.
Yeah. So pointwise convergence is also known for double linear averages, and these two results are all quite old. I think they were proved in the 80s or 90s. Then very recently, this kind of double pointwise convergence has been proved by Mirek, Krause, and Tao, and this was a big breakthrough. This result got published in the Annals of Mathematics. But this is the extent of what we can say about pointwise convergence. So pointwise convergence is a much more difficult question for which very little is known. The methods that are used there are very different. They rely on hardcore harmonic analysis. And in fact, pointwise convergence is not even known for triple linear averages. So we add T3 and here, then pointwise convergence is not known. And proving pointwise convergence of such averages is perhaps the most important open question in pointwise ergodic theory at the moment, or at least one of.
Are there counter examples known when you know that there will not be Pointwise convergence.
That's so counterexamples for pointwise convergence. So for instance, when you study pointwise convergence, there's this delicate question of what assumption you put on the functions. So for instance, for this kind of single polynomial average, it's known that pointwise convergence fails if f is only L1, but there is pointwise convergence if f is L3 for any p greater than 1. So this kind of counterexamples are known, where you restrict the range of functions that you look at. But in terms of restricting maybe the polynomials, then no. And it's expected generally that pointwise convergence will hold. It's just that the amount of technicality that have to be resolved is vast, and no one has been able to do this. So the motivating question behind this talk today is, what can we actually say about the L2 limit of such averages? Because I said already that the L2 limit exists. This has been proved by Walsh. I stated that we have a multiple recurrence result for such averages, but can we say something explicit about what this limit looks like? So how do we give an explicit description of the limit? When you look at mean ergodic theorem or pointwise ergodic theorem for the usual Berkeley averages, then we know explicitly what the limit is. In general, for multiple ergodic averages, this is not possible. You cannot find a single description for what the limit would be. So instead, we try to describe limits in a different way. And there are two approaches. One is more dynamical, another is more analytic in nature. The dynamical approach is to find a factor of a system, by which I mean an invariant T-invariant sigma algebra, or a semi-norm on the space of bounded functions, such that the limit goes to 0 in L2 whenever the function is either orthogonal to this factor or has a 0 semi-norm. And if this is the case, then we say that the factor or the semi-norm controls or is characteristic for the average in question. So the factor approach is, as I said, more dynamical. It allows us to replace, if we can find a factor for which this holds, we can replace the functions in the average by their projections onto respective characteristic factors. And then we can hope to use the structure of the factor in order to say something stronger about what the limit is. The semi-norm approach is more analytic and it's also more general, because each factor gives rise to a semi-norm. So if we have a factor, we can, so if I have a factor, let's say y, I can define a semi-norm, which vanishes whenever the function is orthogonal to this factor. So this would be the kind of semi-norm that you can look at. So each factor induces a semi-norm, but the converse is not true. There are plenty of semi-norms which can be used to control such averages, but which do not give rise to any factor which would be related or associated with this semi-norm. Yeah.
I want to ask you a slide before, but I got distracted. So you are talking about convergence in L2 and pointwise convergence. So the natural question is any research going for other types of convergence? I know a measure or reconvergence or whatever you want to choose.
I don't know much about this. I know that Bergelson has some papers where he looks at other notions of convergence, so also not necessarily Cesaro convergence, convergence of Cesaro averages, but some other notions of convergence, but I do not know too much about this. Mostly because
it's not very popular.
It's not very popular. There are only a handful of people who do like this. Yeah, the bulk of the work goes into either L2 or pointwise stuff. And these are two different communities of people, by the way.
Yeah, I assume this is all because of this is somehow connected. Well, not somehow. This is definitely connected to like number theory and things like that. So if you look at pointwise, this is very very close to number theory. If you look at L2, this is still interesting.
Well, both of these things require a strong number theoretic input, and I'll give some indication later on of what kind of number theory.
And I assume if you look like things like weak convergence, then this connection to number theory, doesn't disappear, but it starts to be less.
Yeah, but no one really looks separately at weak convergence these days, because usually we can prove strong convergence if we can prove weak convergence. So there is not much need to study weak convergence separately. So for this factor approach here that I mentioned, this dates back to Furstenberg, his original proof of Furstenberg's multiple recurrence theorem, which gave a dynamical proof of Szemerédi theorem, already used this factor approach, and then has been refined by subsequent people in further works on the subject. Before I'll state some of the results here, let me very briefly introduce some of the machinery that these results rely on. So a spectacular breakthrough in this field has been achieved in Host and Cry in the early 2000s, who proved L2 convergence of these multiple ergodic averages. And one of the tools that they used was a new family of seminorms on the space of L-infinity functions that they defined. So these seminorms correspond to a given transformation, and they are indexed by natural numbers, as here is a natural number. And so Host and Cry showed that if we take a multiple ergodic average like this, where all the functions are bounded by 1 in L infinity, then we can bound the L2 limit from above by some absolute constant times what we now call a Host plus seminorm of degree k of any of the functions involved. So in particular, if any of the functions has a vanishing Host plus seminorm of this degree, then the average will go to 0 in L2. And these kind of results they rely purely on some van der Korput type tricks, and they can be generalized vastly. So for instance, we know that a similar result holds for polynomials. If we look at multiple ergodic averages with, again, a single transformation T everywhere, and with polynomial iterates, then again, the limit will go to 0 as long as any of the functions has a vanishing Host class seminorm of some degree, where importantly, the degree of the seminorm depends purely on the polynomials, or is bounded in terms of polynomials, and in fact, it can only be bounded in terms of the number of polynomials and their degrees.
But you cannot probably hope for equivalent statements, right?
What kind of equivalent statement?
So of the type that, well, if this converges to 0, then I can say something about the norm.
I don't know, but I don't also see much utility for this. So for linear averages, maybe you could. Actually, in some ways, you can get some kind of converse. For polynomials, I don't really see much use for this. But these seminorms are also defined in terms of some multiple ergodic averages, except that the configurations in terms of which they're defined are somehow cubic in nature. So somehow vanishing of seminorms also means that some multiple ergodic average is 0. So all of these results here that I've mentioned so far, let me emphasize, they are for averages of a single transformation. So we don't have T1 through Tk here, we just have the same transformation everywhere. And this has been state of the art for a very long time. And what I'll try to tell later on about is what we can say when we have commuting transformations, so several different transformations in the average. But before I do this, let me now say a bit more about factors. So Host and Cracow first defined this family of seminorms, but then they also define a corresponding family of factors, which satisfy the following property. So a degree S seminorm is 0, if and only if the function f is orthogonal to the factor of degree s minus 1. And here this is, importantly, this is an equivalence. This goes in both directions. And also Host-Cracow seminorms satisfy this kind of monotonicity property that low degree seminorms are bounded by high degree seminorms. And this monotonicity property gives rise to a similar monotonicity property of factors. So low degree factors are contained in high degree factors. And we get this kind of hierarchy of Host-Cracow factors here. The reason why these factors proved so useful to them is because we can give them some very explicit algebraic structure. So for instance, the factor Z0 is simply the invariant factor, the factor of the sigma algebra of sets which are invariant under the transformation T. And so in particular, if t is ergodic, then this is equal to the trivial factor up to sets of measure 0. And in this case, in particular, the conditional expectation with respect to this factor is simply the integral of the function. If t is ergodic, then the next factor in this hierarchy, so the z1 factor, is what we call the Kronecker factor of the system. One way to describe what it is that this is the smallest sigma algebra with respect to which eigenfunctions of the transformation t are measurable. And an alternative description is that this is the highest factor of the system that somehow captures all the rotational behavior that you have in the system. So in particular, the Kronecker factor is trivial even only if the system has no factor which would be a rotation, and even only if the transformation is weak mixing. Because being weakly mixing is equivalent to having no eigenfunctions apart from constant functions. So for the first two factors, we can give these very nice descriptions. For higher values of S, this becomes much more complicated. And what Holst and Cracow proved is that if t is ergodic, then the zs factor is an inverse limit of systems that we call S-terminal systems. I'll not define here what they are because I'll not really use them throughout the talk, but these are systems that come from S-step nilpotent groups. So these are homogeneous spaces of actions of S-step nilpotent Lie groups, and they have some very strong, very rigid algebraic properties that Holst and Cracow then used to show convergence of multiple ergodic averages. Yeah, and then this last result is, as I said, it's very deep, and it's what we often call Holst-Cracow structure theorem. And when we deal with polynomials, there's one more factor which is relevant, and which, at least in the literature on this subject, we often call the rational Kronecker factor. So this is the factor which is generated by functions that are invariant under some power of the transformation. In other words, this is the join of the invariant factors of t, t squared, t cubed, and all the other higher powers of t. And to give you a sense of how this factor behaves, let me look at two extreme examples. On one hand, let's look at the irrational rotation on the torus. And we know that this transformation is ergodic. In fact, every power of it is ergodic. And because of that, the rational Kronecker factor in this case is the same as the invariant factor, and they're both equal to the trivial factor up to sets of measure 0. So in particular, the projection of any function onto the rational Kronecker factor and also on the invariant factor are just equal to the integral of f. So this is one end of the spectrum. The other end of the spectrum is when we have a periodic rotation. So a rotation of this form on z mod n z. This is always ergodic, but when n is greater than 1, then t to the n is ergodic, is not ergodic, but it equals the identity. So in particular, if n is greater than 1, then the invariant factor of the system is the trivial factor, but the rational Kronecker is the full discrete sigma algebra. And this is because every set or every function is invariant under the power of t to the n. So in this case, projection onto the rational Kronecker doesn't give us anything different. It's just function itself, because rational Kronecker is the full factor, whereas the projection to the invariant factor is the integral of f because of ergodicity of t. And in this hierarchy of Holst-Cracow factors, the rational Kronecker lies between z0, so the invariant factor, and z1, which is Kronecker when t is ergodic. Because whereas the Kronecker factor captures all the rotational behavior of the system, rational Kronecker captures all the periodic rotations which kind of appear inside the system. That's why it's somewhere in between. So this is the kind of background on factors that are relevant when it comes to studying these multiple ergodic averages. And let me now show you one example that illustrates where and how these factors come up. So let's look at the simplest possible example of an ergodic average along polynomials, which is different from Berkeley averages. And these are averages along squares. So in general, for averages along squares, mean ergodic theorem fails in the sense that these averages do converge in L2, but they do not converge to the integral of f when t is ergodic. And here is one simple example. Let's take a rotation of the set of 3 points. And if you compute the limit very explicitly, you can get that the limit of this ergodic average is this kind of function. So where does this come from? To evaluate what the limit is for the system, we just need to understand how squares behave modulo 3. And when n is equal to 0, then n squared is also equal to 0 modulo 3. Whereas in the other two cases, n squared will be equal to 1 modulo 3. So one of the 3 times n squared will be 0, and this corresponds to the first term in the limit, whereas 2 out of 3 times it will be equal to 1, and this corresponds to the second term in the limit. And in general, this is for general f, this is non-constant. This is different from the integral of f, which is just the average over this 3-point orbit. And so we do not get mean ergodic theorem because of counterexamples of this form. And these things we often refer to as local obstructions, and they have to do with the fact that polynomials are not uniformly distributed in cyclic groups. Now, this issue does not appear at all if our transformation is totally ergodic, by which I mean that all the powers of t are ergodic. In this case, no local obstructions appear inside the system, and so we do get convergence to the integral in L2 still. However, for general t, this is not the case. For general t, the best we can say is that the L2 limit goes to 0 whenever the function is orthogonal to the rational Kronecker. And so in particular, the limit of this will be the same as the limit where f is replaced by its projection onto the rational Kronecker. And if we want to evaluate what is the limit with the projection of f onto the rational Kronecker, then we have to understand exactly what are the kind of periodic factors of the system. And this is in general pretty complicated. So this is a simple example where we have a single polynomial average, and it shows kind of quite naturally how the rational Kronecker factor comes into play. So let me now summarize briefly state of the art for multiple ergodic averages along polynomials in which we only have to deal with one transformations. So in general, we do know that these averages are always controlled by some Hochschild seminorm, as long as all polynomials are distinct and the differences between, so all polynomials are distinct, well, let me put it this way. All the polynomials are non-constant and all the differences between polynomials are non-constant. In this case, we know that this average goes to 0 in L2 as long as any of the functions has a vanishing Hochschild seminorm of sufficiently high degree, where the degree, as I said, only depends on the degrees of the polynomials and their number. In very special cases, we can say much more. So for instance, when the polynomials are linearly independent, then Frantzikinakis and Kuca showed about 15 years ago that the rational Kronecker is characteristic for this average, meaning that it goes to 0 if any of the functions is orthogonal to the rational Kronecker factor. So in particular, in this case, if the transformation is totally ergodic and if the polynomials are linearly independent, then this average will converge to the product of integrals of individual functions. So we get some very nice limiting formula. If the polynomials are quadratically independent in some appropriate sense, meaning that they do not satisfy any kind of quadratic algebraic relations of some explicit form, then we can similarly say that the Z1 factor is characteristic, which, to remind you, in the ergodic case is the Kronecker factor. And this was one of the things that I was doing in my PhD. Among many other results, we can also look at what happens when the transformation has some mixing properties, and in particular it's an old result of Bergelson that the transformation is weakly mixing, then this limit will always converge to the product of integrals. So once again, we get, in this case, a very nice limiting formula. So this is the state of the art for averages along a single transformation, and these are by now classical results. Most of them have been proved 2 decades ago, or even earlier than that.
Regarding your result,
Yeah.
let's try to replace quadrat by a higher degree. Is there some conjecture?
The conjecture is that if it's, let's say, independent of degree s+1, then the zs factor will be characteristic. But and I proved some special cases of this, but there are some extra issues that appear and which have to do with orbits of along polynomials on Lie manifolds. I haven't been able to understand this case fully, so I haven't been able to resolve this conjecture either.
So this would correspond to like classical questions about the distribution of polynomials on Lie manifolds that are open.
That are still open, yes. Yeah, explicitly, like you want to know explicitly what is the Lie manifold on which the orbit equidistributes. Well, it turns out that if you have some even quadratic algebraic relations between polynomials, then the orbit is not what you would expect to be, that the full orbit can be contained inside, strictly, can be a proper sub-Lie manifold of the kind of natural Lie manifold where you would expect the sequence to equidistribute. And trying to describe the sub-Lie manifold where it equidistributes turns out to be quite difficult. It has to do with also some very difficult or difficult looking questions on certain algebraic relations that polynomials satisfy, which I haven't been able to do, Nikos hasn't been able to do, and yeah, I don't know if anyone has. I can tell you more if you want about it later, but yeah, it's an interesting thing that I came up within my PhD, and yeah, there are some even though we thought that these orbits are well understood, it turns out that they're not as well understood as we would like.
So the question, could you remind what characteristic means?
So this means that the average goes to 0 whenever a function is orthogonal to this factor. So it has conditional expectation 0 with respect to this factor. Okay, so let's now look at the proper topic of this talk, which is the same multiple ergodic averages, except that we now have commuting transformations. And so before, because I have looked at this, there were some results about this, but very limited, and in even various simple-looking special cases remain unresolved, and we've been largely able to prove a lot of the things which were eluding so far. So here's a kind of summary of things that we did, and later on I'll give more details on each of this point. So for instance, when the polynomials are linearly independent, or when the transformations are all weak mixing, then we gave some very explicit limiting formulas for what these limits would be, similar to what I showed you on the previous slides. We also gave optimal lower bounds for intersections of this point for various special cases of polynomials. So by optimal lower bounds, I mean it's been a question to understand, open question to understand for which polynomials these intersections on average have size as large as something like this for each epsilon. So for instance, if the transformations are weak mixing, then you expect the average of these intersections to converge to this term. And one of the questions that has been studied for quite some time is when can you get at least almost as much? So when do the averages of this have size at least that? And so we also gave some results on this. This is often known under the umbrella term of getting optimal multiple recurrence. or finding popular common differences. To get all of this, we've showed that in general, except some degenerate special cases, these averages are also controlled by Hochsquare seminorms and Hochsquare factors, which up to now was largely unknown. And we also
I wonder in some simple cases, can this be reduced to the case of one transformation? Say you have k copies of x, you make t acting by t1 on the first, t2, etc. In case this happens to be ergodic, can this be used?
So this is a natural thing to try, but if you try to embed this into a single product system of the forms that you gave, then note that you will be looking at orbits of the following form, whereas on the product system what we have are orbits of the following form. So that embedding into the product system that you're suggesting only forces us to look at this diagonal set, which has measure 0, and so we cannot really deduce any result about several transformations from results of single transformation.
Yeah. When you said in this context, the Hochsquare seminorms, are these seminorms that are now defined with T1, T2?
Only those seminorms which are defined in terms of one transformation. So as I said, we showed that these averages are controlled by Hochsquare seminorms modulo some degenerate cases. So for instance, when you look at averages corresponding to, let's say, T1n, T2n, then we do know in general that the classical Hochsquare seminorms are not able to control averages along this. But I'll give more details later on, but as long as, for instance, the polynomials that you have here are pairwise linearly independent, or as long as the composition of T1, T2 inverse has some ergodicity property, you can still control these averages by the usual Hochsquare seminorms, which correspond just to one transformation. So you need to impose some assumptions in the general case, which are immediately kind of necessary, but what we've shown is that once you make these necessary assumptions, then you can get Hochsquare seminorm control. And yeah, the last question that we studied, which I'll talk at the end, is when do we get convergence of these averages to the product of integral? So this question is known in the literature as the question of joint ergodicity, and we also characterized completely when this happens, which I'll state later on. So this is the summary, and let's now look into these results in details. So let's start with the case when all the polynomials are linearly independent. What we showed here is that if the transformations are all totally ergodic, then we do get convergence to the product of integrals. And in the case of a single transformation, this has been proved before by Nikos Frantzikinakis and by Brian Akra. But in the case of commuting transformation, this result was not known. It was known when the polynomials were assumed to have distinct degrees. This was proved by Frantzikinakis and Host about 10 years ago. When as soon as the polynomials are allowed to have the same degrees, so for instance, in this case, the result was not known, and pretty much nothing was known in this case. So this is a kind of model case that we showed, that if the transformations are totally ergodic, then the L2 limit of this thing is just the product of the integrals. Now, when you deal with just one transformation, you don't really lose much by assuming that you have ergodicity, because you can always pass to ergodic components using ergodic decomposition. So for most questions that you can be interested in with regards to these multiple ergodic averages, assuming ergodicity of one transformation is completely costless. However, the moment you deal with several transformations, this becomes impossible. The reason being is that it's perfectly imaginable for one transformation to be ergodic, but for another not to be, and there's no version of ergodic decomposition which will allow you to take all the transformations to be simultaneously ergodic. So this is one reason why studying several commuting transformations is much more difficult than studying just one transformation. You don't get ergodicity, and you have to take care of all the kind of invariant functions which are invariant with respect to some transformations but not the others. And in this general case, we showed that the factors, the rational Kronecker factors over respective transformations are characteristic for this average, in the sense that this average will go to 0 if the fj function is orthogonal to the rational Kronecker factor of the tj transformation. So this is the natural generalization of this result to the non-ergodic case. And let me also mention here that this rational Kronecker that I defined at the beginning may look scary, but for all the practical purposes, all the combinatorial purposes, for instance, that we might be interested in, having a result of this form is just perfect, because we know how to deal with the rational Kronecker factors. We can use some standard approximation tricks to get some nice results the moment we know that a certain average is controlled by the rational Kroneckers. So this is the first of our results. And let me explain briefly why for a result of this form we need some kind of linear independence on the polynomials. And I'll explain this with a counterexample. So here we have the simplest counterexample possible. We have a double average with the same transformation. The transformation I'll just take here to be an ergodic rotation on the torus, and let's define the complex exponential. The point is that once the polynomials are linearly independent, we can use the linear dependency to get rid of n from this product altogether. So for instance, here we can take functions f1 and f2 to be the following powers of the complex exponential. And then a simple computation shows that if you look at the product of these two terms, then n gets cancelled out. And so the product here is just the complex exponential. This holds for every n. So in particular, this average equals and converges to the complex exponential. So in particular, it has a non-constant limit. And so it's immediate from this that it cannot, the limit cannot take a form like this, which is constant. So the point about linear dependence and linear independence is that if we have linear dependence, we are able to construct counterexamples which prevent this from happening. And if we have more complicated algebraic relations between the polynomials here, then we can construct even more complicated counterexamples, and we can, in this case, say even less about how the limit of such average behaves. And yeah, here are some corollaries about the optimal multiple recurrence that can be deduced kind of almost immediately by some standard tricks from the result before. So as a corollary, for instance, we showed that if we have linearly independent integral polynomials and a subset, a measurable set of positive measure, then the average of these intersections is at least this much for maybe not the average is at least this much, but for a positive proportion of values of n, this intersection can be bounded. The measure of this intersection can be bounded from below by this quantity, and explicitly this holds for what we call a synthetic set of values of n. So a set. This means that the set of n for which this holds intersects every interval of some finite length L, where L is fixed. So this is a very strong statement. This means that for many n, this kind of inequality is satisfied, and this has an immediate combinatorial corollary, which can be deduced from this by the Furstenberg correspondence principle. And namely that if we take a set of ZD with positive upper density, if we take any choice of directions in ZD and any epsilon, then the positive upper density, which is this D bar here, of the following intersection now has size at least at least that much. So yeah, as I said this before, this is often what we refer to as optimal multiple recurrence, because it tells us that for many values of n, the intersection, either in the dynamical setting or in the combinatorial setting, is as big as we would expect if things were completely random.
But is it possible to say something about this L?
Not using the dynamical methods. So using the dynamical methods, you just know that it would be synthetic, but I don't think you can get any quantitative dependence. So getting a result of this form also is, there are people in combinatorics who try to get these results using Fourier analytic methods. And I think that quantitative results that they have would allow you to bound L in terms of epsilon and in terms of the density of the original set. But these quantitative results are only known in very few special cases. So, yeah.
But you would believe that they exist, that they are true.
I think that yeah, using quantitative approaches, this should be perfectly possible. But yeah, so dynamically we cannot really get quantitative dependencies, so this would require a very different toolbox. Yes, so there was a question before about number theory that comes into this. So let me mention two kind of main inputs, two main properties really that come into these results. So the reason why we can get these explicit limiting formulas for independent polynomials is because we know from the Walsh equidistribution theorem that if we have linearly independent polynomials, then any linear combination where at least one of the weights is irrational will be equidistributed on the torus. And equivalently on the at the level of exponential sums, what this tells us is that the following exponential sum in this case goes to 0. And these exponential sums actually come up very naturally in our argument. So at the very end, kind of, we're showing that everything reduces to studying these exponential sums. And since we get that these exponential sums go to 0, we are able to go back and prove that we get this very nice limiting formula when the polynomials are linearly independent. And this by the way, this only happens when polynomials are linearly independent, or when you can say something about the eigenvalues of the system. But the second input that we use, and which is independent from the first one, is that we can control these averages by Hofstra seminorms, except in some degenerate cases that I mentioned. And so more explicitly, what we're showing in this direction is that as long as the polynomials that we take are pairwise linearly independent, meaning that any two of them are linearly independent, then this average can be controlled by some Hofstra seminorm. And again, the degree of the seminorm here is completely independent of the functions, it's completely independent on the system that we look at. It only depends on the number of polynomials and their degree, or at least it can be bounded in terms of this number. And so this is really one of the kind of big chunks of things that we proved. And this is much stronger than whatever existed before, because before, in the case of commuting transformation, a result of this form was only known in a very special case when the polynomials have distinct degrees. And what we showed is that as long as polynomials are linearly independent, pairwise linearly independent, this holds. So for instance, the result of this form was not even known for this kind of average. And this is what we started with. We were able to get it for this, and then after months of kind of pushing it further and further, we eventually arrived at the result of this form. And as an immediate corollary of this result, we get a very nice limiting formula in the case when the transformations are weakly mixing. So now, if the polynomials are pairwise linearly independent, and if the transformations are all weakly mixing, then what we're showing is that this average does converge to the product of integrals of the functions. And again, in the case of a simple transformation, this has been proved 40 years ago by Bergelson, but for commuting transformations, this is a completely new result. And the reason why this follows immediately from the previous result is that for weakly mixing transformations, host class seminorms get a very nice formula. In this case, all the host class seminorms are just the absolute values of the integral. And so by using this fact, by using the fact that the average goes to 0 when any of the functions, or when at least one of the functions has a vanishing host class seminorm, and by using a simple telescopic identity, we can get this nice limiting formulas.
Can you comment, because as you said, the result was now for distinct degree polynomial.
Yeah.
So what is the new idea here? I mean, what is the difference?
So I'll maybe tell you differently. I'll tell you what is the main issue that previously was there and that we didn't know how to deal with. So, for instance, for the average that I stated on the previous slide, which takes this form. So the issue that appears is that if you do you know how the ped induction scheme works roughly? Mm-hmm. So there is this the way these results are proved that you are able to control an average by a host class seminorm. They are usually proved by many applications of the van der Kolk inequality, where you start with some average, and you at each step you apply van der Kolk inequality to reduce it to something of smaller complexity. And the idea is that after finitely many times of doing this, you arrive at the linear average, and then for linear averages we know how to deal with them. So the problem here is that since these polynomials have the same degree, what happens is that, for instance, if you compose it with t1 minus n squared, then you'll get, what you would get is something like, let's say some f1 tilde here, and here you would get something of this form. Maybe let me write it as a weak limit, so let me write it in this form. Then if I compose it with this transformation, then this equals to f1. In this case, I don't need to define anything new here. This will just be so these two things are equal after a change of variables. So I replace x by this, and t1, and then t1 disappears from here completely. That's why I'm pushing f1 here. On this function, we'll then get t1 minus n squared acting here. And then if we include this t1 minus n squared inside here, then the problem is that the main term, the term that corresponds to the highest degree polynomial, now depends not only on the function, on the transformation t2, but it depends on the this composition of t2, t1 inverse. So at the end of the day, if you wanted to repeat the same procedure as you would apply when you deal with averages of a single transformation, what you would get is that this average is controlled by some seminorm of f2, which depends not only on the transformation t2, but also on these transformations t2, t1 inverse. So these are the kind of seminorms that I think you asked me before, so seminorms which are defined in terms of several transformations. And the problem is that in itself, this might still look nice, but this is too weak to tell us much more about what the average is. So the main thing that we had to do is to show that as long as we can control our average by this kind of seminorm, this kind of mixed seminorm, when you have two different transformations, then we can upgrade it to controlling the average by a seminorm in terms of the transformation T2 purely. And the reason why these appear again is because when you do some change of variables, you see that you get these mixed transformations kind of naturally. So our main idea was how to pass from this kind of seminorm to the usual whole square seminorm defined purely in terms of T2. And this is, well, a pretty long argument which uses some kind of induction, but it doesn't use any deep tools. Like it doesn't use, for instance, any structure theorem. The only thing that we're using is that if we have usual whole square seminorm, then you can write them down as an integral of f times what they call these dual functions. And this is the only structure theorem that we used. And so, for instance, this theorem works not only if you look at z actions, but at more general, I think, countable Abelian groups or something actions. Yeah, so I don't want to go into more details because it gets super technical, but this is the issue that appears. You have to deal with these things, and our main idea was how to get rid of these things. Any further questions before I move on? Yeah, so this result is stated, and the previous result was also stated under the assumption of pairwise linear independence of polynomials. But let me also mention that in a second paper that we wrote, we upgraded our techniques, and we could also deal with averages where polynomials where we had the same polynomials but with different transformations. So an example of what you can see here. In order to show that these kind of averages are controlled by whole square seminorms, you need to make some assumptions though on the transformations. Because for instance, in this case, if the transformation T1 and T2 becomes the same, then this average would become degenerate. It would just become something like this. And the problem is that for the tools that we're using, we could only bound such an average in terms of a seminorm of f1 times f2, which is not good for any applications, and not in terms of the seminorm of the individual functions. So to preclude some cases, we have to say something about the composition of T1 T2 inverse, or T1 inverse T2, which is the same. So in particular, we can do anything that we want with these averages as long as T1 inverse T2 is ergodic. But more than that, and the necessary, and more than that, we can handle them as long as the invariant factor of this composition takes this form, which means that the only functions that are invariant under this composition are those that are simultaneously invariant under T1 and T2. So it's not difficult to see that this is a necessary assumption for us to be able to do anything nice with these averages. But we also show that this is sufficient, that as long as we have this condition on the transformations, we can do pretty much whatever we want with these averages. So for instance, under the same assumption, you can handle average where we have T1n and T2n. And we can show that this average is controlled by whole square seminorms, as long as the condition of this form is satisfied. But let me not spend too much time on this case. in the last, I don't know, 10-15 minutes, I'll try to discuss one more question, which is related to what I said before, but also interesting on its own. So before I'll do this, let me say that if I have a sequence of transformations on like probability space, then I say that it is ergodic if these kind of averages converge to the integral of f in L2. And let's say I want this to hold for all L infinity function f. So in particular, a sequence t to the power of n will be ergodic even only if the transformation t is ergodic. So this notion of ergodicity naturally of a sequence of transformations naturally extends the ergodicity of a single transformation. And one of the things that has been studied in ergodic theory is for which sequences you get what we call joint ergodicity. So we say that some integer sequences are jointly ergodic for a certain system if for every bounded function this average converges to the product of integrals in L2. So joint ergodicity really combines two ideas. First, we want each of the transformations to be individually ergodic. But second, we want to get this kind of probabilistic independence of on average. This is how I like to think about this, that if you take the average, then in the long run, these orbits behave independently of each other, and we get convergence to the product of integrals. So this notion has been, to the best of my knowledge, first studied by Bergelson and Bergelson already in the 80s. They were looking at joint ergodicity of this kind of simple average, and they showed that this is jointly ergodic even only if the following conditions are satisfied. So first, the product transformation has to be ergodic on the product space. And second, the composition of any two transformations has to be ergodic. So the fact that these are necessary conditions is the easy direction, but showing that there are sufficient conditions for this to hold is the difficult direction here. And motivated by this, there has been this general question for which sequences can we get joint ergodicity. And there is a natural kind of hypothesis, natural conjecture or question maybe that we expect the sequences to be jointly ergodic for the system if this kind of product action is ergodic on the product space, in the sense that that on the product space, the integral of this with respect to any function converges to the integral, and that each of these compositions are also, each of these composition actions is ergodic. So these conditions are natural generalizations of these two conditions when the iterates that we have here are different. So the question is for which sequences this conjecture holds, and maybe I don't want to say that. Maybe I don't want to say that I expect this to hold for any kind of integer sequences. I'm pretty sure that there are some counterexamples, but what we would expect is that for some kind of naturally occurring sequences, this conjecture will be satisfied.
So for the first, if you can say, so for the theorem of Bergelson, you assume that T1 and Tk commute?
Yes. So this is for commuting. Everything here is for commuting transformations.
And the same in the question, you also want you guys to commute.
Yeah, exactly. So one of the things that we proved is we gave a general criterion for when sequences are jointly ergodic for a certain system. And we showed that we get joint ergodicity even only if the following three conditions are satisfied. So first, we want each of the transformations to be individually ergodic. And it's not difficult to see that this condition is necessary, because for instance, if T1 is not ergodic, then I can take a non-constant invariant function f1, and then if I set everything else to be, every other function to be 1, then this average will just equal to the non-constant invariant function f1. So in particular, it will be different from it will not be constant, it will be different from the product of integrals. So the ergodicity, this assumption is kind of necessary. The second condition is that I want this average to be controlled by some host cross-segment. in the sense that there exists S such that the average converges to 0 for all the functions such that at least one of them has a vanishing Hofstra-Segnorm of degree S. And again, this condition is immediately necessary because joint ergodicity is equivalent to the fact that the average is controlled by the degree 1 Hofstra-Segnorm. And the second condition is that this identity holds whenever the functions are eigenfunctions of the respective transformations, which translates to the statement that for all eigenvalues of the respective transformations, such that not all of them are 1, the following average will equal to 0. Now, for measure-preserving transformations, we know that eigenvalues lie on the unit circle. So really the last statement is a statement about exponential sums. And again, it's necessary because it corresponds to a special case of this condition. So all of these three conditions are necessary for almost trivial reasons. But what we showed is that they're not just necessary, they're also sufficient. As long as they're satisfied, we do get joint ergodicity.
Do you mean here that these operators Tj are from transformations? Isn't it the same Hilbert space? Because everything that's written here is in the L2 Hilbert space. Operators.
So I don't know if I don't know about the result, whether something like this could be expected in the Hilbert space, and I also don't know whether some of the tools that we use could be translated to the Hilbert space setting. So in short, I have no idea. I haven't thought about these kind of questions.
Maybe I should say that there is a book which I haven't read, which is called Operator Theoretic Aspects of Ergodic Theory by Eisner, Farkas, Hassen.
This was my question.
So maybe that's a good point to look for such results, but I don't know what the experience are.
So yeah, I don't know. It's possible, but it's an uncharted territory. And let me also say maybe why these kind of conditions are useful to study joint ergodicity. So first, this is just a statement about exponential sums, and if we can't deal with the exponential sums corresponding to these sequences, then certainly we cannot deal with these averages in general. But quite often we can deal with exponential sums without being able to deal with the corresponding ergodic averages. So dealing with this rather than this is a significant simplification. Second, well, to show that something is controlled by Hofstra-Segnorms, there are many methods for showing this, and the methods that we have are quite robust. They can deal with a lot of sequences. So this condition is also often much easier to check than a general condition like this. So each of these two conditions separately is much easier to check than the full thing. And the statement about ergodicity is usually something that we know. We know whether a certain transformation is ergodic or not. And in fact, to prove some of our other results, for instance, in order to prove that that this happens, so that for linearly independent polynomials and total ergodic transformations we get this convergence, we use this criterion. So we use the fact that, as I said, that we know that these averages are controlled by Hofstra-Segnorms, and then we use this criterion that we proved together with the exponential sum estimates that we have on linearly independent polynomials to get this nice limiting formula. So we don't just prove some criterion; we also apply it for things that interest us. And an added benefit is that in order to apply this criterion, we don't have to deal with any new manifolds. So especially for people who know new manifolds quite well, understanding orbits of various actions on new manifolds is often a hugely difficult thing and very technical thing to do. Whereas here we only have to do with eigenvalues, So with rotations, the simplest examples of Riemann inference. And in fact, we prove something much stronger. So we don't just give a criterion for when this average converges to the product of integrals, but we also give a criterion for when it converges to the product of conditional expectations.
Excuse me, how does your result compare to the conjecture you gave the slide before? Question.
This result?
No, to the question.
The question. I'll answer this in a moment.
Okay.
Yeah. Yeah, so this is a criterion which is, I would say it's more natural than this question, but this question, let's say, has historical importance. And we actually show that this holds for polynomials using this criterion, which is one of the last things that I'll talk about. Yeah. But yeah, what I started saying is that we get something stronger. We get a criterion for when such an average converges to the product of conditional expectations. And as I said before, and let me reiterate, when we deal with several commuting transformations, we cannot assume that they're simultaneously ergodic. So this is getting a criterion for this kind of convergence is a much stronger and much more general thing than getting a criterion for this kind of convergence. And it's also more difficult to prove this than to prove this. We obtain this as a special case of the other thing. And yeah, for a single transformation, this kind of criterion was given by Nikos himself first, and then together we extended it to commuting transformations. But we had to deal with many more things than showed up just for a single transformation. And yeah, referring to the question that Jonathan asked, using this criterion, we were able to give a complete characterization on in fact, several different characterizations for when we get this kind of convergence for polynomials. So among other things, we showed that this conjecture from one of the previous slides holds for polynomials. So that for polynomials, this average converges to the product of integrals in L2, even only if these two polynomial actions are ergodic. I'll also give another characterization of this fact in terms of eigenvalues of the transformations, which is, in my opinion, more natural, but which I didn't state here because it was maybe a bit too technical. And for the last thing, let me state that a lot of the things that I discussed here can also be extended to the combinatorial setting. So there are all these works that use dynamical approach to additive combinatorics and to number theory. But at the same time, recently there has been a lot of progress on the combinatorial side of things. So using Fourier analytic methods, various people have been able to obtain very nice quantitative results about related to the polynomial Szemerédi theorem. And so, for instance, by adapting these ergodic methods and techniques to the combinatorial setting, I proved the following results about polynomial progressions in subsets of cyclic groups raised to an appropriate power. So what I showed is that if I have linearly independent integral polynomials, and if I have some direction vectors in ZD, then each subset of Z mod n Z, the power of D, where n is sufficiently large prime, each subset of this space lacking a polynomial progression of the following form has at most that many elements. So in particular, all large subsets of the space have to contain a polynomial progression of this form, and in fact, they have to contain many polynomial progressions of this form. And as I said, this here is somewhat out of context, but there have been many other related results to this. So when D is 1, so when we have to deal with only a single dimension, then this result has been proved by Pelouse about 5 years ago. And this has been a very groundbreaking result in the field because of the new techniques that Pelouse introduced.
What is C?
C is some absolute constant. So it's an absolute constant which depends only on the degrees of the polynomials and the number of polynomials.
I didn't understand your comment about the technique of the proof. Is this some kind of mix? So you're using dynamics and Fourier?
No. But so the good thing about a lot of these techniques in the ergodic theory is that they don't really rely on ergodic theory that much. And perhaps because of this, one could hope for some Hilbert space extensions of some of these results.
So this was proven by the dynamical?
No, this was proven without any dynamics, but a lot of the techniques that we introduced in ergodic theory can be just taken directly from ergodic theory to combinatorics and translated in a natural manner, because they're really analytic techniques. They're not combinatorial, they're not dynamical, they are analytic, and because of this, they can be repeated in many contexts. So there is this interplay of ideas recently, and a lot of the techniques introduced in ergodic theory have found their analogs in combinatorics and vice versa. So, for instance, one of the big components that we used in our proofs with Nikos was a technique introduced by Sarah Pelous in her work on the single-dimensional case of this result. I don't know if you remember from band level whether people have mentioned this or not, but Pelous introduced a technique that we now call a degree lowering technique, which shows that if you can control something by a degree S host-class seminorm, then you can control it by degree S minus 1 also, under some conditions, and then you can go down like this to show that you can control your average by, let's say, degree 1 or degree 2 seminorm. So this technique originated in combinatorics. It does not use anything except for the inverse theorem for the Gauer's norm of degree 2, which is the usual inverse theorem which relates the degree 2 Gauer's norm to eigenfunctions, and has a natural analog in the ergodic setting.
But C depends on polynomials.
Yes, but it doesn't. It only depends on the degrees of polynomials, and it only depends on the number of polynomials. So. Well, okay, as long as polynomials have bounded terms. So let's say that it depends on polynomials, but usually in these questions we are interested in some fixed polynomials. So for instance, here the prototypical example would be something like this. The prototypical example, which I should have written but I didn't, is a configuration of this form. So we have fixed polynomials, n squared and n squared plus n. The direction vectors would be, here is the direction in the horizontal direction, here is in the vertical one. But for instance, C doesn't depend on the direction. So for each direction, you get some kind of uniform result. Yeah, so there is a rich interplay of ideas, and there will hopefully continue to be in the years to come. And this is just a glimpse of what can be done using, well, in a different framework. And that's it for me, so thank you very much.
Are there any questions?
Any remaining questions?
Maybe I have a quick question. So, in any situation, for example, here, when you have under some extra assumptions, get rid of the integral condition that says this condition that the p of 0 is 0. So can you add the shift?
Yeah, so actually here they have to be, here the condition is that in the cyclic group setting, that the polynomials without the constant term have to be linearly independent.
Okay.
So if I add, I don't know, 1 to whatever here, it still works, it's still fine. In the integer setting, this is a bit more delicate because you can get some, again, local abstractions. So for instance, in the integer setting, it's known that if you look at even a 2-point pattern of this form, then you cannot find it in the set of multiples of 3 because this is never divisible by 3. But in a cyclic group setting, these things don't really appear.
Any other questions, maybe online? Adam?
No question. But thank you for the talk.
Okay, so maybe I'll ask a question. You know, usually people in such contexts, they ask, okay, if you assume that these transformations are not commuting, but are generating a nilpotent group.
This is the next step. I'm planning to look at it once I finish some current things, but yeah, I want to.
But is it true that this is like the most general context where you would expect? Because after this there are some counterexamples, right?
Yeah. So even when you deal with solvable groups of transformations, I know that people have counterexamples. I think Bergelson and Leibman and maybe Furstenberg also have some counterexamples, but things don't work. Whereas in the nilpotent setting, so far there are no counterexamples in the nilpotent setting, so everything that has worked for a simple transformation or for commuting transformations has also been known to work in the nilpotent setting. So we have multiple recurrence, for instance, when the transformations are nilpotent. This is an old result of Leibman. I mean, old, 20 years ago, but all right. We have convergence when we deal with nilpotent group of transformations. This is the level of generality at which Walsh proved L2 convergence. Recently, there are even some pointwise convergence for results for just single averages, but in this form. So I think they are able to get pointwise convergence here, where the transformations generate a two-step nilpotent group. They're working on the higher step case. So here we have a product of transformations acting on one function. And this is due to Mariusz Mirel and some other people. Rai Ionescu, I think, and someone else. Yeah, so we don't have any counterexamples for nilpotent things, and for that reason, at least I expect that everything would follow through. Now, the technical difficulties in trying to extend it are enormous, and so far, at least for me, for the things that I tried, even in the simplest possible examples, like, for instance, even for averages of this form, when T1 and T2 generate a two-step nilpotent group, even for this, I haven't been able to prove things. But I expect them to.
So can continue this a little bit. So has anyone looked at all at these questions for looking, say, polynomials for non-amenable actions? So for example, you take the free group, okay, you do not have the usual averages, but you have Nebo-Steiner and all this business of looking at the averages over spheres and.
Well, my level of understanding ends at ZD actions.
Okay.
And then I know that when we are on new manifolds, we have a nilpotent group action.
Okay.
And I had no literally nothing else. So I wouldn't know.
Okay, so let's thank Borys.